Okay, everyone, we got some homework to catch up on from the last few days. Page 683, we had a number of questions there. We need to go over number 8, 15, and 17. Let's go over number 8 first. Let's explain the effect of wavelength on the index of refraction for a particular medium like glass. How does this lead to dispersion? Explain the effect of wavelength on the index of refraction. Well, we talked a little bit about the effect of frequency on index of refraction. Well, we know that the effect of wavelength is going to be exactly the opposite, right? So if frequency has one effect, wavelength is going to have the exact opposite effect. Here's how I remember this, guys. It's not a matter of memorizing the effect of wavelength on the index of refraction. I draw the picture, and then I figure it out. Okay, so I have white light. White light strikes the prism. We know that that white light splits up, and we know that it splits up so that red is on the top and violet is on the bottom. Roy G. Biv. Well, red light has the lowest frequency. Well, red light has the highest wavelength. So red light is a high wavelength, violet light is a low wavelength. How does wavelength affect the index of refraction? Well, the higher the wavelength, the blank the index of refraction. Bigger or smaller? Smaller. The higher the wavelength, the smaller the index of refraction. That causes the red light to bend less than the violet light. That make sense? How does this lead to dispersion? Well, if there's a different index of refraction for each different color, then of course we're going to get a different amount of bending for each different color, and therefore it's going to split up. Let's take a look at 15 now. It says, using a ray diagram, determine the image attributes for an object located at 2f, 2 times the focal length, relative to a converging lens. Let's draw a principal axis here. We've got a converging lens, so it's going to be a convex lens. We're going to put the optical center right there. We're going to put the focal point right there. We're going to put 2f right there. On the other side, we're going to draw in the focal point in 2f as well, even though in the end, you know that there's not really a focal point on the left-hand side. Okay, it's just a spacer. We're going to put our object at 2f. Now we're going to draw the ray diagram. First ray, hopefully I have the distances good here so that it works out. First ray parallel to the principal axis, down through the focal point. Second ray is going to go down through the optical center. Going to more or less work out here. The image is going to be formed right here. What are the attributes or the characteristics of this image? Bigger? If I bring my fingers over here, it appears to be pretty much the same size. Okay, had I drawn this perfectly to scale, it should be exactly same size. So it's same size, it's inverted clearly, and it's real, right? We could project this onto a screen. It's solid lines that intersect. Okay? And finally, number 17, it says red light of wavelength 700 nanometers and blue light of wavelength 475 nanometers are both incident on a lucite block. Which color will be refracted to a greater extent? This is a question that's actually quite a bit like question number 8, the one we already did, right? Here's the prism. Let's actually change that a little bit. Let's make it black. We have red light and blue light incident on the lucite block. Let's say we have all colors of light incident on the lucite block. Here's all colors. What happens? Well, they split up because there's a different index of refraction for each different color. Well, we know that red light splits up or bends the least, and violet light bends the most. So which color will be refracted to a greater extent? Violet. It's the one with the higher frequency. It's the one with the lower wavelength. It's the one that produces the bigger index of refraction. So how do you answer both of those questions? Don't memorize anything except this diagram. Okay, except that cover of the Pink Floyd album. Which album was it? Dark Side of the Moon? Okay, that had the prism on the front. Yeah, how many people know that? How many people have seen that? Just about everybody. Wow. I'm impressed for people your age to know that album. That's even like before my time even. Sorry? Yeah, it's just so old though. All right, guys. We also had some worksheet questions. You can see the answers to the first 3 worksheet questions up there now. Just take a quick peek. Finally, question number 4. All right, guys, request to go over question 1 and 3. Number 1 says a 12 centimeter tall object is placed 15 centimeters in front of a converging lens. First thing I'm going to circle is this whole converging lens thing. That tells us that it's a positive focal point. Listen, if it's converging and you don't circle it, you're probably going to get away with it, right? When it's really important to circle it is when it's diverging, okay? Because that's when you have to make it a negative focal point, and that's when, if you forget to do anything with it, you're going to make a mistake. If you forget to do anything with this one, well, in the end, you're going to make it positive, and that's what it should be. Has a focal length of 10 centimeters. Okay, that's going to be our focal length, and it's going to be a positive value. This, by the way, is going to be HO, and this is going to be DO. HO is positive. It doesn't say it's upright, but we'll assume that it is. The object distance is always going to be positive. We want to determine the image distance. We want to determine the image height, the magnification, and the attributes, which we're going to get from those things that we just solved for. So let's get one of those things now. Doesn't matter which one comes first. Okay? In the end, if we're looking for 3 things, odds are we're going to use both of the equations that we have. So let's just start with one. Okay? The one that I usually start off with, if I'm not sure which one I should start off with, is this one, because this one almost always gets us something. So start with that one, if you're not sure. 1 over F is equal to 1 over DO, which is 15. Sorry, we know what F is, right? 1 over 10 is equal to 1 over 15 plus 1 over DI. Good. That's going to allow us to get DI, which is the first thing that we're actually looking for. So let's use our little shortcut here. Let's say 10 x to the minus 1, subtract 15 x to the minus 1. Let's get an answer for that. Let's flip it over. And let's get DI is equal to 30. It's positive. That makes life a little bit easier when we go to do our next one here. Okay, DI is 30. Let's say M is equal to negative DI over DO. Negative DI is negative 30 over DO, which was positive 15. We get a magnification here of negative 2.0. What does that tell us if the magnification is neg 2? It tells us not so much that the image is inverted, but it's what? No. Well, it does tell us it's larger because it's a 2, yes. The fact that it's a negative, you're almost right there, Patrick, on the fact that it's inverted. Tristan? Right. So if the object is upright, the image is inverted. If the object is inverted, the object would be upright. So if you take it in context, the fact that the object, we said the object is upright, then yeah, it tells us it's inverted. But looking at it on its own, it doesn't tell us it's inverted. It just tells us that it's flipped over. All right, let's get HI now. Let's say M is equal to HI over HO. By the way, could we have went straight to HI over HO equals negative DI over DO and used those two parts? Sure, we could have. We wouldn't have got M there. We would have got HI right away. And there's an argument for that being actually a better method. Okay, what's the argument for that? Why could that potentially be a better method than what I've just done here? Solve for M and then said M is equal to HI over HO. What if I made a mistake, right? What if I made a mistake in my magnification calculation? All of a sudden, now I'm introducing something else into there, right? So it increases the probability of a mistake. Not hugely, though. I'm not too worried about that. I want to solve for HI here. It's going to be M times HO. It's going to be negative 2.0 times the object height, which is 2.0 centimeters tall. That gives me negative 4.0. Let's get some characteristics or some attributes here now. Number 1, give me one of them. And tell me how you know. Yeah, Mac? Okay, how do you know it's larger? Good. Magnification greater than 1, so we know that it's larger. Good. What's next? It's inverted. How do you know it's inverted? Okay, it's upright to start with, and it's a negative magnification. Or you could look straight at HI. HI says it's negative 4. Either one of those ways tells you it's inverted. Good. And what else? Real or virtual? This is the one that people struggle with a little bit sometimes. Real or virtual? It's real. How do you know? Yep. Was that 12? Oh, goodness. That's what you get for circling your givens. Right? All right, so that's going to change. That's going to change this this one then, right? So it's going to be neg 12. That's going to give me neg 24. Doesn't change the characteristics, right? What about real or virtual now? It's real, and how do you know that? Di is positive, right? Good. All right. And the other one that we needed to go over was number 3. So it says the image created from a 10 centimeter tall upright object. Okay, that's going to be HO. It's placed 5 centimeters. The image created from this object that is placed 5 centimeters, that's going to be DO. Okay, it's not the image that's placed 5 centimeters. It's the 10 centimeter tall upright object that's placed 5 centimeters. Wait a second. What's that? Oh, the image, right, yeah. The image created is 4 centimeters tall. That's kind of a little bit crazy wording there, right? A little bit confusing. The image from this object is this tall. So the image height is 4.0 centimeters. And it's upright, so we're going to make it positive. We want to find the magnification. We want to find the image distance. We want to find the focal length, the attributes, and the type of lens. But when we calculate these things, then we're going to get all of those things out of it, right, from the signs that we get from these answers. Okay, not sure which equation to start off with. I'm going to start off with this one. Although there's no real good reason why we start off with this one other than as opposed to the other one. 1 over f is equal to 1 over 5.0 plus, oh, we don't know that, do we? Okay, I guess I picked the wrong one to start with. That's okay. Let's go back to the other one. Let's say m is equal to hi over ho. Hi is 4.00. Ho is 10. All right, the magnification is 0.4. That still doesn't allow me to go into my lens equation to determine what f is. But I can now say m is equal to negative di over do. Di is equal to negative m times do. Negative 0.40 times the object distance here, which is 5. Give negative 2.0 centimeters. The image distance is negative 2 centimeters. Haven't made any mistakes on this one, have I? This one's good. Now we can find the focal length. 1 over f is equal to 1 over 5.0 plus 1 over negative 2.0. Let's pull out the calculator and use our little trick here. Let's say 5, x to the minus 1. Let's say subtract 2x to the minus 1. Could I have said 5x to the minus 1 plus negative 2x to the minus 1? It's the same thing, isn't it? I just saved myself one keystroke, that's all. Okay, let's flip that over. And we end up getting negative 3.33. All right. First of all, what kind of lens is it? It's diverging. How do you know that? Negative focal length. Good. What are the characteristics of this, the image that's produced by this diverging lens? Same as the characteristics that are always produced by a diverging lens, right? It's smaller. We know that because m is less than 1. What else? It's virtual. How do you know that? Di is negative, and it's upright. How do you know that? I think we're told that, weren't we? We're told that. Yeah. Yeah. Good? You guys feel comfortable with these lenses? All right, guys, on Wednesday when I was at the track meet, you guys saw a podcast on diffraction. You said diffraction, we said diffraction is the spreading out of a wave around a barrier or around an opening. Okay, sound waves diffract around the opening of the door so that when I'm standing right here and somebody's walking down the hallway, they can hear me not just when they're in front of the door, but they can hear me when they're down the hallway a little bit as well. Sound waves diffract. All waves diffract. Well, guess what? Light waves diffract as well. Okay, that's more evidence to support that light is a wave. The very first day that we introduced this unit on electromagnetic radiation, we said diffraction was one of those 4 properties of waves that's exhibited by electromagnetic radiation that supports the wave nature of light. Guess what? Interference was another one. When we get 2 waves coming together, we get interference, either constructive interference or destructive interference. Well, when we get diffraction taking place in 2 places, you get 2 waves formed now. Those 2 waves will interfere with each other, and it's kind of a crazy interference pattern that ends up being produced. I'm not going to go through all the little dots like I did in the podcast about where you get a big crest and a big trough and so on, but the bottom line is you end up getting constructive interference right here. You end up getting destructive interference right here. You end up getting constructive interference right here, and so on. So you get these alternating areas of constructive and destructive interference. Now, if these are water waves, we can see them. We can physically see the interference in the water waves. If they're light waves, we can't, because the light's not reflecting off of anything. The activity that you guys did yesterday when we shone the laser light at the block of glass, okay, there was nothing to see until it hit and reflected off of the block of glass. That's why you had to look at the little point as opposed to just draw the line where you saw the beam. You didn't see the laser beam. If you had smoke in there or something, you might see the laser beam. Otherwise, you're not going to. So how do we see this interference pattern? With water waves, we just see it by looking at it. With light waves, we have to put a screen down here. When we put a screen down here, we're going to get a bright spot there. Right? We had constructive interference, big crests, big troughs. There's going to be a bright spot. You get more light. But then right next to it, you get a dark spot because there's no light. Then you get a bright spot because there's constructive interference. Then there's destructive interference, you get a dark spot, and then a bright spot, and then a dark spot, and then a bright spot, and so on. We get alternating areas of bright spots and dark spots, all corresponding to constructive and destructive interference. Now that bright spot in the middle, we call our central antinode, our central bright spot, our central maximum, whatever you want to call it, our central. We assign it a number of 0. This would be our first order maximum, or a first order bright spot, or a first order antinode, second order bright spot, third order maximum, first order maximum, second order antinode, third order bright spot, whatever you want to call it, right? Any of those things mean the same thing. Make sense? In between, this would be our first order minimum, our second order minimum, our third order minimum. First order min, second order min, third order min, fourth order min, and so on. Or you could say first order dark spot, or first order node, or something like that. All right? Now, when we have, let's draw this out again here. Here's the screen. Here's the openings. And here's our bright spots and our dark spots. Zero, central, first order, second order, third order, first order, second order, third order, fourth order. We got some variables that we've got to identify here. And they go with these 2 equations that we have on the board here right now, the 2 equations that you saw on Monday. Okay, the first one that we want to identify here is lambda. That's the easy one. Lambda is the wavelength of the light. Whatever color of light you use has a certain wavelength. Lambda is that wavelength. Easy, right? D is the second one that we want to identify. D in both of these equations means the same thing. D is always the distance between the openings. That's going to be a small distance. The distance between the centers of the openings is going to be D. And it's going to be in what units? It should be in meters, although technically, as long as you're consistent in this equation, units end up canceling out again. So if you use centimeters, you'd get away with it, as long as you were consistent. But you know what? In this equation, let's go with meters. Okay, let's always go with meters. So D is that distance between the openings. Okay, that's identified. Now let's look at L. L, I usually label as a capital L, because I don't want you to get mixed up with a 1. Okay, in your equation, though, it shows it as a lowercase l. It's the distance from the openings to the screen. And that's going to be a much bigger number than D is, much bigger number than D. So if you start getting mixed up as to which one's which, and you see one that's bigger, it's going to be L. Okay, L is almost certainly going to be the biggest number for distance that we have. What's next? Well, let's look at X. This is the tricky one, because X could be this, the distance between the first order max and the fourth order max. It could be the distance between the second and the third order max, or it could be the distance between the first order minimum and the second order maximum. It can be whatever we want. It doesn't matter where it is. You can label it wherever you want. The trick is, if you're going to make X whatever you want, you got to make N consistent with that. N is going to be, in this case, N would be 3. 4 minus 1 is 3. In this case, N would be 1. 3 minus 2 is 1. In this case, N would be, what would it be in this case? 2.5. 2 minus negative 0.5, 2 minus negative 0.5 gives me 2.5. So it doesn't matter what X is, Maddie. It doesn't matter what X is, as long as N is consistent with X. Does that make sense? All right, only one more variable, theta. Theta is almost like X. Sometimes I say it doesn't matter what theta is, where theta is measured, as long as N is consistent with it. Well, it does kind of matter, because theta has to be measured always from the central. X doesn't. X can be measured wherever you want. Theta has to be measured from the central maximum. So we'll measure it from the central maximum to the second order maximum, or to the second order minimum, or to the fourth order minimum. Doesn't matter, as long as N is consistent with it. In this case, N would be equal to what? 2 minus 0 is 2. In this case, N would be equal to what? 1.5. 1.5 minus 0 is 1.5. Does it make sense? Diffraction interference of light. This is also, by the way, known as Young's double slit experiment. So if you ever see that term Young's double slit experiment, that's what we're talking about. It was performed by a guy named Thomas Young. Okay? So he's the guy that made this kind of experiment famous and saw this interference pattern. Good? All right, so there's our two equations here. Essentially, it comes down to recognizing what you got, plugging the numbers in, solving. There is a little caveat, though, to this, and I can't remember if I mentioned that in the podcast yesterday or not. This equation is an approximation. It's not perfect. Okay? It's an approximation that works when the angle is below about 10 degrees. It works very well when the angle is below about 10 degrees. But above 10 degrees, it's not so good. It's not such a good equation. So there's times when we're not going to want to use it. The vast majority of the time, it's fine. But there's that odd time when we can't use it. You know what, though? I don't want to go and calculate the angle every single time. If I'm going to calculate the angle every single time, then I might as well just use this equation to begin with, right? So how am I going to know whether it's valid or not? The rule of thumb, just hold on for a second. The rule of thumb that I want you to use is this. If L is greater than 10 times X, we're good to go. Okay? Now, that's a bit of a conservative rule here. Okay? You could get away with a little bit more. Okay? Or a little bit less, I should say. If L was slightly smaller than that, you'd get away with it. But that's going to be our rule. Okay? Because that's a nice, easy rule. It's easier to say 10 times than 9.4 times or whatever it ends up really being. Okay? So, if L is greater than 10 times X, you're good to go. Every time you see a question where you want to use that equation, just check. Just check. Is L more than 10 times X? If it is, then use that equation. If it's not, then listen, you're going to have to use this equation, but you're going to need angle to do that. Here's L, here's X. How do you get the angle? The inverse tan function, right? Get the angle and use that equation, okay? If you didn't finish up those questions that we assigned on Wednesday, when I was at the track meet, let's give them a try again with the review that we've done here today. If you struggle with them, watch the podcast again, or come and see me on Tuesday, okay? Quiz on Tuesday, quiz on Tuesday on lenses, right? On lenses. It's going to be a tough one too, guys. Hey, going to be a tough quiz on Tuesday.